In this lecture, we're going to discuss safety issues associated with biomedical instrumentation and biomedical measurements lab. There are a number of issues that can impact both patients and the physicians or clinicians that are at the scene or on the site. When it comes to electrical safety, it's primarily the patient that's at risk. So in this first lecture on safety, we'll discuss issues associated with patient safety when instrumentation is present in the environment. The slides for this presentation are taken from the textbook. This chapter is written by Walter Olson. So we first need to understand that there are physiological effects that are associated with electricity. And for a physiological effect to occur, the body has to become a part of an electric circuit. In other words, current's got to enter the body at one point and leave at some other point. The magnitude of the current is obviously equal to the applied voltage divided by the sum of all of the impedances of the body tissues in series and the two interfaces at the entry points. Now, typically, the largest impedance that's seen is the skin resistance at the contact surface. The skin is often covered with skin oils, which have a fairly good resistive property. Three phenomena can occur when electric current flows through biological tissue. The first of these is that there is electric stimulation of excitable tissue like nerve and muscle. The second is that there is resistive heating of tissue, and the third, electrochemical burns and tissue damage for direct current and very high voltages. I have been shocked in the lab one time. The kind of shock that I received was 60 hertz, just AC current. It was on one arm, and I was very fortunate because it basically was the kind of situation where it pinched some skin. So it went in one part of the skin and out the other part of the skin on my upper arm, just an area of about half an inch. But even with that, I still definitely felt muscle spasm, quite a bit of nerve pain, and some heart palpitations. So sometimes small shocks from 60 hertz can be much more significant than we think. And I actually did also have a little burn where the current entered and left, you could see on the skin. So here is a figure that illustrates what are some of the physiological effects of electricity. And this is for 60 hertz current with an RMS value that varies logarithmically from a milliamp to 100 amps. And so you can see that between 1 milliamp and 10 milliamps, we're right at the threshold of perception. So threshold of perception is where you can detect that there's current present. And these vary from 2 to 10 milliamps. You'll get a slight warming of your skin. You'll feel the presence of the current. The next part of the range is the let-go current. The let-go current is defined as the maximum current at which the subject can withdraw voluntarily. When you, especially on the hand, touch something that is hot, electrically hot, it's going to cause a muscle contraction. And typically, if you touch something with the inside of your hand will contract around whatever it is you're clutching. And so what they're meaning is voluntary withdrawal means that that is not so severe that you can't open your hand and let go of the object that's shocking you. So the minimum threshold for the let go current is 6 milliamps. So even higher in current, then you start to get ventricular fibrillation, which is really the main reason typically that people die from electric shock. You can also get respiratory paralysis, fatigue, and pain. Typically, respiratory arrest occurs between 18 and 22 milliamps. And this is basically just because of severe muscle contraction that you get asphyxiated. So if the magnitude of the current is sufficient to excite only part of the heart muscle, then you get normal propagation of electric activity in the heart muscle that's disrupted. If it's disrupted sufficiently, you can get a heart rate as high as 300 beats per millisecond as you get these waves of depolarization that sort of randomly sweep over the heart ventricles. In the United States, there are approximately 1,000 deaths per year in accidents that involve cord-connected appliances. Now, when the current gets high enough, the entire heart muscle contracts. So although the heart stops beating while the current's applied, if the current's interrupted, a normal rhythm resumes. So ventricular fibrillation would be when you have a part of the heart that is excited and it causes these irregular beats. That can be corrected with a defibrillator circuit, which basically resets the entire heart potential. This, when the entire heart muscle contracts, if the current's not removed, you basically have a sustained myocardial contraction, and so you don't have a heartbeat. Once we get above 10 amps, you have resistive heating. And so the current here becomes a problem because you can get pretty severe burns. You can actually get explosion of body tissue. And so typically what gets people is not the voltage, it's the current. Voltage is greater than 240 volts can puncture the skin. As soon as the skin is punctured, then you've got all kinds of problems that occur with any kind of excitable tissue, any kind of nerves. Suddenly they become conductors throughout the entire body. So keeping the skin intact is extremely important. And so resistive heating will usually occur at the skin because that's where the resistance is higher. So your I squared R is significantly higher there. We don't know a lot about the effects of current in excess of 10 amps, particularly currents of short duration. There is a body of work done by the Pulse Power people who have looked at electrical safety and looked at things like total energy deposited as well as time of short current pulses. And so there's some research that was done in the 80s and early 90s on that, but obviously you can't do that research on people. And as a general rule, if people are not in the biomedical field, there aren't a lot of animal models. So there's not a lot of crossover between people who work with short duration pulses and the biomedical community looking at safety. So here are just some distributions of sort of when you begin to perceive things. Men and women are different. Both the perception current and the let go current is different. It tends to be lower for women than it is for men. So no idea why that's true. Women tend to have a higher percentage of body fat than men, and it could be that that's a better conductor and transmitter to the muscle or to the nerves. But I didn't find any references on why the gender difference. But as a general rule, you can see the threshold of perception, typically about a milliamp, and the let go current range somewhere between 6 and 16, depending on gender and other things. So here's a let go current versus frequency. So here is 60 hertz right here. You can see, interestingly enough, that there's a minimum that occurs between 10 and 100 hertz, which means, of course, that at the frequencies of electric transmission in the US and Europe, that's actually the most dangerous. It has the lowest let go current threshold. As frequencies increase, you see that the let go current increases, and so you're more likely to be able to withdraw from a dangerous situation before permanent damage is done as frequencies get higher, or even as frequencies get lower than, say, 10 hertz. So unfortunately, our frequency of energy transmission and power transmission is probably the most dangerous that it could possibly be as far as ability to do damage to human beings. So figure 14.4 gives you an indication of sort of what the stimulation current threshold is for short duration. And that basically the threshold is inversely related to the pulse duration. by the strength duration equation. So I sub R is the actual current. I sub D is sort of this current threshold when you begin to have cardiovascular effects. D is the duration, and tau is the time constant. So here is an example of how this equation is used. You basically have a cardiac pacemaker company, and they want to deliver short pulses. They want the current to be basically 3 times um, the threshold current. They want to know what is the duration. So if the cardiac membrane has a time constant of 2 milliseconds, basically you can plug a 1 in for ID, a 3 in for IR, and then you can solve this equation. And so on solving that equation, then you basically get that the duration is 0.8 milliseconds. So it's important, first of all, there are lots of things unknown here. Cardiac membrane time constants. People actually have really measured electrical properties of cardiac membrane in the lab uh, after autopsy, and a lot is also done with pig hearts because pig heart's fairly similar to the human heart in some of its electrical characteristics. So pig hearts are commonly used as models of the human heart, and so they can be kept active and measurements can be made to get some of these numbers. Anyway, not asking you to design cardiac pacemakers, just thought it was interesting that they in fact can be designed to have a certain duration. So when current's applied to the body, 2 different things can happen just depending on the situation. At 2 points on the surface of the body, like from hand to hand or hand to foot, you only actually get a small portion of the current that flows through the heart. So one of the things they used to tell us in the lab, in the pulse power lab, was always put one hand in your pocket. Because as you can see here, if you have a connection on both sides of the body, the current flows straight through the heart. So they used to always say, put your left hand in your pocket, use your right hand so the current will flow from your hand probably through the foot to ground. These kind of currents pretty much are large, and they're externally applied, and these are called macro shocks. When the current's applied on the surface of the body, you have to have a much higher current to actually cause heart fibrillation than if current goes inside the body. So the other situation is, and let me just reemphasize that the importance of the location of the 2 entry points is often overlooked. So for example, in my case that I described earlier, where I got a little shock to the upper arm, I had an entry part on the upper arm and exit part on the upper arm, exit point on the upper arm. So basically the current in my body just flowed right here and was localized to this arm. This person in the figure, you can see they have an entry point on one hand and exit point on the other hand, so current's going to flow through the body. Now, the good thing about this is that it does distribute itself. So you have a smaller current density at any one place. And remember, this is a resisted path all the way through. So you have a longer path, meaning you're going to have a greater resistance. The bad thing is that it does pass through the heart. So the location is important, and if you have 2 points on the same extremity, the risk of going into ventricular fibrillation is fairly small, even if the currents are high. Now you get quite a bit of protection by the skin, and sometimes that can be the very procedures that are there to help the patient can actually create a problem by reducing the skin resistance. So sometimes if you have medical procedures that have required that you use conductive gels or that you pass conducting devices into natural openings, if you have skin incisions, skin abrasions, or gels present for an electrode, those are intended to lower the resistivity of the body. And so when you do that, you definitely, or the resistivity of the skin. So when you do that, you definitely have created a situation where this natural protection of the skin is reduced. So this other figure shows a microshock, and I believe I have a better slide. Yeah, so you're particularly vulnerable to electric shock in the situation shown in figure 14.6b. So in this case, you actually have a catheter that's passed through the arm and into the heart. And basically that provides a conductive path directly to the heart. It's insulated because the catheter is passed through an insulating material. So there's no current that flows anywhere until you get right to the heart. So in this case, because all of the current is making it to the heart, you can have very small currents. And the very small currents are called microshocks, and these can induce ventricular fibrillation. So in this case, all the current flows through that conductive device. The current density at the point of contact can be very high. And so in dogs, for example, you can get microshock fibrillation in currents as low as 20 microamps. Typically, the accepted safety limit to prevent microshocks is 10 microamps or lower. So you can see the difference in the macro shock, external to the body, current spreads out, is very diffuse in the body, and there's a large voltage drop at the skin, large resistance at the skin, which reduces the current. Versus the micro shock, where right at the catheter tip is where all of, or right at whatever the device is, right at the point of contact is where all of the current's present. Current density is very high at this point. There's virtually no resistance between the device and the heart itself, and no path length to stop or absorb some of the energy. So all of the energy is provided right at the heart, which of course would be the most dangerous situation. And you can certainly have catheters and devices in other parts of the body, but this one clearly would create the greatest danger. So when thinking about design of systems, there are some things that can be done, and there are also some things that are specified by the National Electric Code. So here is just kind of a simplified schematic drawing of a typical electric power distribution system. As a general rule, you have about 4,800 volts that come from the substation and enter into a commercial building, usually via underground cables. And then you have a step-down transformer that typically provides 240 volts. Now, some equipment requires all 240 volts, and so it is possible to take from the positive to ground and get the 240 volts. But most appliances and ordinary things will operate on 120. So typically the transformer secondary winding is center tapped. The top and bottom connections are ungrounded, and a ground is placed in the middle. And this is typically an earth ground, which is normally to a water pipe. In some situations, the earth ground is actually a physical copper pipe driven into the ground. We're not discussing imaging in this particular safety video, but in MRI systems, because those voltages are so high, there is a physical copper rod that is driven into the ground as opposed to trying to ground on the water piping in the building. So that earth ground is formed, and then all of the wiring and outlets are done using 3 terminal outlets, and they've got this separate wire. So you have your hot wire, which is black, and you have your neutral wire, which is white. And if you live in an older home, you may have a receptacle that only has 2 plugs, one for hot, one for neutral. But in more modern homes, or homes that have had new wiring put in, you will always have a 3rd plug, which is your ground. That ground is the earth ground. The neutral wire is also tied to the earth ground, but what the green wire does is it allows you directly from the earth ground to also ground the chassis and any metal surfaces that are present in the room. So an additional redundant ground path often through a metal raceway or a conduit or separate cabling, is typically required in patient care areas. Sometimes older installations use like a metal conduit as the only ground conductor. Typically, that's considered unsatisfactory because you can get a lot of loose conduit connections as well as corrosions. So, what you really want to see is you really want to see a hard wire. Often that's done to the patient area, to the bed where the patient is, and then there's just a hard ground that makes sure that everything is safely grounded. So you can actually have a shock hazard that exists between the two conductors that supply an appliance. Now the neutral wire is connected to ground, and because of that, a connection between the hot conductor and any grounded object poses a shock hazard. You can have microshocks if sufficient potentials exist between exposed conductive surfaces in the patient's environment. And so there are some maximum potentials that are permitted according to the National Electric Code. In general care areas, the maximum potential permitted between any two exposed conductive surfaces would be 500 millivolts and under. In critical care areas, it would be 400 millivolts under normal operation. 40 millivolts under normal operation. The reason it's different is that in general care areas, you generally will have very little contact with electrical devices. You tend to be maybe hooked up to a heart monitor, maybe a blood pressure machine, and that's about it. In critical care areas, there tends to be, and you may not even be hooked up to a heart monitor. In critical care areas, there tends to be a lot more exposure between conducting surfaces and the body. There's more potential for coming into contact with hot wires and surfaces, and so because of the greater potential for that, the specification for exposed wiring potential differences is significantly lower. So it's a risk analysis kind of procedure. Also, it is required to have periodic testing for continuity between the patient ground and all grounded surfaces. So you can have things that happen like, ground planes or ground wires get disrupted, corroded, somehow disconnected, and then that exposes the patient and the patient's treatment area to potential shock. So even when things are grounded, things can go wrong because you can have what's known as a ground fault. And so in that case, you would have a ground fault from a hot line to an instrumentation chassis or case. So here's a typical electric circuit. You've got a circuit breaker, and if high current does flow, the circuit breaker is going to open, but there is a certain time associated with that. In this case, you can see that you have a piece of electrical equipment. It's connected to the patient. In this case, if there is a fault, what's happening is the hot wire is shorting out to the chassis, creating a voltage on the chassis that then flows because the patient is grounded. Then that current will flow from the chassis through the patient to the ground in whatever path is the path of least resistance. So that's a problem because that means if you short out to your chassis, that's a problem. So here is the 3-wire circuit that has the hard ground. In this case, the hard ground or the green wire is actually connected to the chassis itself. So there's a direct short from the chassis to the building ground. Because that is almost always a much lower resistant path than the path through the patient, any faults that occur will typically flow back through the green wire to the building ground. So the grounded chassis can make quite a bit of a difference in a potential macro shock. So the macro shocks due to ground faults can be minimized when you have this third wire in your plug that is the green wire, that is the ground wire, that provides a separate path because it connects directly to the chassis. Whereas the black and white wire would connect to whatever instrumentation or measurement device is being used. Now, microshocks can also occur. As a general rule, these occur through catheter type devices. The most deadly ones are when the catheter is placed in the heart, which is the most common use of catheters in surgery that connect to some sort of electrical device. So you can see in this case, figure A, you have an intact ground. When you have an intact ground and there's a short to the chassis, then it basically flows through the intact ground back to the ground in the building. When the ground is broken, then any fault that occurs in current being in the chassis has nowhere to go except through the patient to ground, because the ground connection is broken. And so you can have up to 100 microamps flowing through the heart. When you have a broken ground, you can also have current flowing through the heart in the opposite direction. It just depends on if the catheter is a part of the chassis or not. So those are some significant issues that can occur when you have ground faults. Now, there are a number of ways that you can have electrical connections to the heart. And so these are just some examples of some of the ways that can happen. You can have epicardial or endocardial electrodes that have some kind of externalized temporary cardiac pacemaker. So this would not be an implanted pacemaker. This would be a pacemaker that has an external power supply that is then connected to things outside of the patient and ultimately connected to the electrical supply system in the building. You can have electrodes for making measurements that are internal to the heart. And so these are actually electrodes that penetrate the skin and are making a measurement of tissue activity inside the body. And so you can basically have a connection that occurs that way. You can also have liquid-filled catheters that are placed in the heart to withdraw blood, measure blood pressure, or inject substances like dyes or drugs into the heart. So one thing to remind people of is that a patient's only in danger of microshock if there is an actual electric connection to the heart. The internal resistance of liquid-filled catheters is much greater than the resistance of metal conductors and pacemakers and electrode leads. So internal resistance of the body is only about 300 ohms. Resistance of the skin can be hugely variable. So just to summarize, microshocks occur under some of these conditions when something is implanted in the body, usually at or near the heart, whereas macroshocks tend to occur when connections are made outside of the body. So even when you install a very good grounding system with ground fault detectors and other things, you can't 100% prevent possibly hazardous voltages that can result. So if you have this ground fault between a hot conductor and ground, this can inject large currents into the grounding system. This is unusual, but it can happen. Typically, the circuit breakers open quickly, so that's why that time of duration measurement is so important, because it gives you an indication of how long does this situation have to exist before the patient is irreparably harmed. So in order to mitigate this problem, you basically provide a system that isolates your electrical instrumentation from the actual power supply. And that's accomplished using an isolation transformer. So here's an example of an isolation transformer. You have your primary, which comes in with your hot and your neutral wire. And then you have your secondary, which also comes in with a hot and neutral wire. But you notice that the ground wire, which is connected on the primary side to the isolation transformer, and is not connected to the secondary side. And so what happens here is that if you have a single isolated ground fault, that can occur to either conductor. And so that occurs in your power system side. If you get a fault from either conductor to ground, then basically you just revert to a normal grounded system. Whereas, and so you're kind of, once again, it's a risk management thing. You're assuming that it would be highly unlikely for you to have a fault in both sides of the system. It's a very low risk thing anyway, and so if it were to happen on both the primary and the secondary side, that would be almost unknown. This has been used for a long time to provide safety for electrical instrumentation as well. So you're less likely, in the event of a ground fault, you're less likely to have damage to your instrumentation if you're using an isolation transformer. So every piece of instrumentation that's used, typically if you're using an EEG or an EKG, typically all that instrumentation contains within it an isolation transformer. So usually individual instruments contain their own, plugged into an isolation transformer of their own. And then sometimes there's even a double layer of safety where the power entering the room in general is isolated through an isolation transformer. So that is typically a way that is used to address ground faults. It can also address things like lightning or some other external force that enters the building and somehow increases the potential on the ground. Here are some examples of acceptable levels of leakage currents through the chassis. So you can see that they're given in microamps, and typically they vary from, for the chassis itself, acceptable currents on the chassis would be around 100 microamps, and you remember that's pretty much below the detection limit. At the patient lead in microamps, if you have non-isolated leads, then 10 microamps is allowed. The overall range varies from 10 to 100 microamps. And there are some additional specifics that can be found both in the National Electric Code as well as in your textbook for test conditions and requirements that kind of give you an indication. So here's an overview of the safest possible kind of grounding system. In this case, you will notice that you have an overall ground. And this is called a star ground. So typically you would want one point where there is a ground. And so you want that to make a single connection to the building ground. There's a patient equipment grounding point that occurs. And so all of the equipment that is near the patient, including the bed, are grounded to this grounding point. And this is referred to sometimes as a star ground because it has a central point and then everything comes out from that. There is then a single lead that connects that to the building ground. And so that is sort of your reference grounding point. Now, this shown here on the right that says to other patient equipment grounding points can be a little misleading. So I want to be clear that this is not other equipment on this patient. This would be going to other rooms, other beds, and other patient equipment grounding points. So, visualize that the room next door has exactly a similar setup. It would then come back to this building ground. What you do not want, is you do not want another conductor to come out of your building ground, touch some instrumentation in this room, and then be able to contact the patient. Because in that case, you would form a ground loop between this wire, which goes to the patient equipment grounding point, and this wire, which goes to something else in the room. And that can create a problem because ground loops can act as pickup coils and actually induce external voltages. So the safest thing to do is within a room, you have one ground point. Notice that no chassis or bed or anything is directly connected to another chassis. So you would not want, for example, to run a ground wire to this receptacle and then from there ground the bed And then from there, ground some instrumentation. That would also create a ground loop. So you want a wire running from every grounded surface back to this single point. So that's your star ground. And that makes for your most, it both minimizes risk as well as minimizing any noise that would occur due to pickups by ground loops in the building. So that pretty much covers an overview of safety as far as electrical safety. We've specifically addressed the heart, and we've addressed the differences in macroshocks and microshocks. There are a number of additional figures and information in Chapter 14 of your textbook that show things like how measurements are made, how fail-safe circuits are installed, how these systems are tested. We're not going to go over those specifically in this lecture. I am asking you to read Chapter 14 of your textbook, though, so that you see what is possible in the as far as circuits and testing circuits go.